And I think we're live. Okay, we're live. So, and no one's here, so it's just you and me talking, and that's fine. But for those that may drop back to watch the recording of this, it's me, Jesse Kozlowski, and Chris Van Matre, just having a hangout here. And we do have one viewer so far that's joined. Good evening, two viewers. So it's me and Chris. We're going to just talk about some survey stuff. And why don't we get started? We're probably going to do some screen sharing and talk about the project that Chris has been working on out in Utah. But just before we get into all that, I wanted to ask Chris to go ahead and talk about his background, how he got into surveying. And I think this is important for people to see because I had seen comments, that you're not a surveyor and so forth and so on. So this would be a nice opportunity to let people know how long you've been in the profession and what your background is, what you're doing. So take it away, Chris.
Okay. Yeah, my name's Chris Van Matre, and my surveying career started out in 1983 with the Highway and Transportation Department.
In what state?
In Missouri.
Missouri, okay.
So my very first job was to hold a hand level and level the tape. Back in those days, we had a 100-foot chain that we'd use to measure with. And my job was to make sure that the chain was perfectly level. From there, I moved up to rear chainman, lead chainman, and then eventually became instrument person and worked for the Highway and Transportation Department for 12 and a half years up until 96. Moved back here to Colorado where I was born and raised and started working for a little land surveying company about 9 miles from where I grew up. And
that's in Colorado, you say, right?
Yes, I moved back here to Colorado about 9 miles from where I grew up. I found a little surveying job and for a little surveying company, worked there for, I think, 6 years until the owner passed away of a heart attack one evening. The company that bought him out hired me immediately, and I worked for them for, probably 2 years. And another guy hired me for a lot more money, so I worked for him for 4 or 5 years. And then a real good friend of mine started his own business, and I've been working for him for about 9 or 10 years now.
So it's a good long history. And you say you began you said 83?
Yes.
Okay. A couple years after me, I started in 78, right after high school. Oh, by the way, when you worked in Missouri for the district, or that's what I wanted to ask you, what is Missouri DOT divided up into districts?
Yeah, they had 12 districts.
So what district was yours?
I was District 4, I believe. It was Kansas City.
Okay. So then, what year did you first? You were talking when we talked before. You had your background is very similar to mine, starting out with transits and moving on up through the whole toolbox of technology as it came available from EDMs, total stations, and GPS and so forth. Let's talk about that a bit too. I wanted to hear when you first started using GPS and everything. Go ahead and tell us about that.
Okay, so I believe it was 99 when I first started using GPS. We started with Aztec. I don't know if you're familiar with those. They use TDS software.
Yeah. Okay. Yeah. Sure.
So I started off with the Aztec, and then ended up he sold that system, and we went to Trimble, and I've been using Trimble ever since.
Okay. keep talking, because what I'm going to do, I wanted to share this link to my Facebook group so they can tune in too if they want. We have about 7 viewers now. This is good. At some point, I will pull the chat out so I can take a look and see what's going on. Let's see.
Yeah, and like I said, I started off back in the day with the old 22nd non-adjustable legs with a 100-foot chain, and we measured with a 100-foot chain and plumb bobs. So it's basically the same way they done it way back in the 1800s. And it gives you a really good appreciation of the foundation that we work off of, how hard those guys actually worked. It's just mind-boggling.
Absolutely.
The people that have never used any of that older equipment, just use the newer stuff with GPS, probably will never have any comprehension of the amount of work that went into all that stuff.
You know, I really do my best to try to get that across to people. We take it for granted nowadays that, and I've made this point, that we can do in an hour what probably took people weeks or months and maybe years to do. We could survey right over a mountain. We can do a lot of, we can process baselines across the country. So I just laugh at these things. It boggles my mind, just like you said, about what we can do now. It's for sure.
Yeah, most definitely. I can break down a section in about 2 hours with GPS.
And how did it go in the old days? That took weeks, right?
A section probably took an entire day.
Okay. Yeah, I don't have any experience in the sectionalized lands. All my experience is on the East Coast in what we call the meets and bounds state.
Right. There's pros and cons to that. I really like the section work. When I was getting my pilot's license, one of the lady instructors there, her grandfather had a surveying business back east, and she was telling me, she's like, I remember once us having to go out and dig up a wall because the POB, the point of beginning of the survey, started at this wall that was like 2 or 3 feet deep.
Oh, did I just turn off the volume?
You're
still there, right?
Yeah, I'm still here, I believe.
Oh, I was looking at us being broadcasted. It has a delay, so that's all that was. Anyway, that's where I did find the live chat. Let me take a look, see what people are saying here. Doing good, John. John was the first guy in. How you doing? Sue Lynch, hi all. Hey, everybody's just saying hello right now, so that's good. Sorry, I've been a little distracted while you're talking, but of course you and I have already covered some of that. But I've been just trying to get some housekeeping out of the way. I wanted to post this link for others to see, and what I would have rather have been doing is kind of chiming in with you along the way. It sounds to me like our backgrounds are very similar in terms of when we started. Like I said, I started in '78, got out of high school, and back then they had this a work program. You could find jobs in the paper. I really wanted to get out of school and go right to work. That was my, I was not very academic, I could say. So I was not college bound. And I wanted to go to work, and the first job I took out of high school was installing fiberglass insulation. You can imagine what that was like in the summertime. So, so I lasted about a month or two, and I really wanted another job, and there was a job being advertised, a surveyor. Had no idea what that was. You know, what's a surveyor? I don't even, we never learned about anything like that. And that's one of the disadvantages about surveyors, is that they're kind of unknown to the public. The public thinks we are engineers. and,
Yeah.
and they don't know what surveying really is. So anyway, so I went and I read the description of this job. It was outside work. That sounded good. And, got on the job and still didn't really quite get what it was about. And the party chief said, we're going to be looking for some PKs. I had no idea what a PK was. And there we are. We're all kind of kicking pebbles out of the way and walking around. He said, it's going to be a nail. You'll know it when you see it. And finally we find these Parker Kalon nails, and it literally has the letter P and the letter K stamped into the top of it. That is a PK nail. So, yeah. The next thing he said was we are going to go out and find a geodetic monument, a US, he said a USGS monument. I'm like, what the heck's that? And, we're trudging around out in the swamp or out in the marsh in Atlantic City. And, we're out there where all people are just dropping off junk like old washing machines and tires. And all of a sudden we come across this huge chunk of concrete sticking up out of the marsh. And he goes, there it is, and I'm like, I'm looking at it, and there's a disc on the top. And I can still see that disc. It was kind of green. It's a brass disc, but it has weathered, so it's kind of green. And, it says U.S. Coast and Geodetic Survey on it. And I asked him, what the heck is this thing? And he goes, well, it has latitude and longitude on it and elevation. I'm like, what? What are you talking about? I actually was astounded. Like, who put this here? And for what reason? And how did they do it? It really drew me in. I was really mesmerized by it. So I became very fascinated with that. And I literally said to him, you mean to tell me there's more of these? So that I think that was the bug. That was the bite that got me so interested in surveying was that whole thing. So anyway, that was my beginning. And I'm like you. I mean, we started on transits, worked our way up through. I remember when we got our first EDM, electronic distance measuring instrument, and the owner of the company called it the light meter. And we would be traversing miles and miles through the back rural areas of New Jersey and southern Jersey, and before we had the distance meter, the electronic distance meter, we were pulling a 300-foot highway chain, steel tape. And, but those were the days, you had a 3-man crew, sometimes 4, working those days. The birds are chirping, just walking around. I mean, it's hard work, let's face it, but things changed drastically as the technology became more capable, more accurate, let's say, it increased your production. And when that happened, the demands went up for, well, when are you going to deliver? I mean, if you can do it faster in the field, boom, how fast can you turn around and get us our survey? So things changed a lot. And like you were saying just a bit ago, you can break down a whole section corner or a whole section in an hour. And people listening here right now and the general public, they have no idea of what really goes into surveying. And I would say that even though our technology has changed and has made things faster, surveying itself is still the same. Would you agree with that, Chris?
Yeah.
Yeah, we're still licensed to do the same thing. We're licensed to safeguard the public because we're dealing with real property. We're dealing with boundaries of people's lands, and there's a right way to go about doing that. And so, you need to get the experience, and nowadays it's education entirely. A lot of states are going to 4-year degrees to even be considered for taking the exam. So,
yeah, here in Colorado, they're going to that in 2020.
Okay. So they've already put the word out. That means anybody that's out there needs to start applying to get their license. They can get in there now under the rules and regulations that exist now. Once the deadline passes, then you're under a different set of rules. Same thing like here in New Jersey, that rule, 4-year degree rule, was passed, I think, in 89 or 90, right around that time. Are you licensed in Colorado or in Missouri?
I'm not licensed.
Okay. And so there's a lot of people like you that didn't get the license. We have lots and lots of experienced surveyors who obviously they can't hang a shingle up and practice surveying, professionally and charge fees for it, but they work for licensed surveyors like you are working under the license of another surveyor doing the work that he has you doing, right?
Right. Yeah, I could go in and take the test, but I'm like, to me, it's just another piece of paper.
Really?
And I've always told I would never work for a licensed surveyor if I was a licensed surveyor.
All right. So you wouldn't be a license working under a license. You would, if you got your license, that means starting your own business. So you were happy doing what you're doing now. Is that what you're saying?
Exactly.
Okay. Well, let's see. Is there anywhere you want to take this conversation right now?
No, I could hit on one of the points you were talking about just a few minutes ago about how people don't realize what it takes to do surveying. I do a lot of city block breakdowns on surveys, and it's kind of funny. Yeah, people will come out. I'll be looking for their property corner and their lawn, and they'll come out on their lawn and say, "What are you doing?" I'm like, "I'm doing a survey." And they'll be like, "Where are you doing your survey at?" I'd tell them, "On the other corner of the block over here." And the first thing they ask is, "What are you doing over here?"
Yeah.
Well, what I tell them is we can't just find the four corners of a lot or a property. When we do a survey, we actually have to break down and find all the control that we can find in that entire city block to make sure that the pins, if we found the pins at that lot, that they actually fit and they were set correctly.
Roger that. I'm going to go look at the chat while you're talking.
And it's the same for sections. Whenever you do section work, I've had farmers where I got to get access in to get a section corner. They're like, "That thing's been shot 100 times." And I'm like, "Yes, it has, probably has." But every surveyor that does a survey has to remeasure the entire section to break it down. If you got to meet some bounds within that, or whether your legal is called you own the northwest quarter of such and such section.
Right. And so you've got to establish that.
Reestablish it every time.
Right. No, that's real good. Anything else right now? Because I'm ready to kind of maybe move on to some of the stuff that's behind you there on your whiteboard. And also, I noticed you put a hat on that says, we may as well talk about this. The Earth is flat and NASA lied. Okay, well now so this is where, in talking to you, I get the sense that you've got a very good background in surveying. I would tell anybody, it sounds to me like you know what you're doing, you know what you're talking about. Somewhere along the line, you came to the conclusion that the Earth is flat. Do you want to talk about that? How did you arrive at that?
Let's see. It was probably mid-2014.
Okay, about three years ago, let's say. Yeah. 4 years
ago. When I first saw it, I was like, that sounds interesting. When I looked into it, took me to the hollow earth theory, and I was like, yeah, I lost interest with it. But about 3 or 4 days later, I don't know, something hit me. I started thinking about differential leveling. Not only that, how far you can see things that you shouldn't be able to see.
Okay, well, that's one of the things that comes up quite often.
And also, I had my pilot's license, and all the bells and ringers started going off with all my pilot training too.
How so? Like, where do you, what?
Keeping the gyroscopes that you use to keep yourself flat and level as you're flying along, and comparing that to the horizon that I was looking out at. Without the instrument panel, you can fly flat and level just looking out at the horizon.
Okay.
And then they have on almost every airplane, they have what they call a trim wheel, where once you get up to altitude, instead of putting pressure on the yoke back and forward, trying to keep it at the same elevation, it's got a trim wheel that you can set so you can just take your hands off of it and it'll fly straight and level, mile after mile after mile after mile.
Well, there is an altimeter involved, right? Didn't you just set the height that you want to be at?
Not in Cessna. In a Cessna, everything's pretty much manual, except for the trim wheel. You have the trim wheel, so you can basically just take your hands off of it. And you got your altimeter, and you can watch your altimeter. But once you get the plane trimmed out, you can let it fly for mile after mile after mile, straight and level, without ever touching the yoke again or the trim.
Okay. Well, I have no. I can't really comment to that since I have no pilot training. But let's go back to the surveying. So the couple things you raised there that got you to think the Earth was flat was you came across something called the hollow Earth theory. You dismissed it. A couple days later, you thought about it. And what came across your mind was differential leveling. Is that what you said?
Yes, that's the first thing that come across my mind.
And what about differential leveling? What about differential leveling that gets you to think the Earth is flat?
I was like, well, until I found out, I was like, level is level. To me, level is a flat line. But once I come to find out that the explanation of level is, if I set an instrument or a level up here, it's level. If I set an instrument down here, it's considered level. If I set one up here, it's considered level. So level that most surveyors, and as a geodetic surveyor, you consider the level to follow the center mass of the Earth, right?
Well, when you pointed to your whiteboard there and you said down here, you mean down on that drawing?
Down at the bottom, let's say this is.
Well, there, you know, your drawing there, you could say up and down on the drawing, but you know, right now, Chris, just point down, like where you are. No, not on your drawing. Point down.
Oh, down.
Yeah, that's down.
So let's say if I set up a level at the North Pole, it's level. If I set up the level at the equator, it's actually sideways, but it's still considered level.
Sideways to what?
Sideways to the ball, the Earth.
Well, I mean, are you talking about like holding a globe up in the room and looking at it?
Exactly.
Yeah.
So
go ahead.
So that's why I drew this. Let's say this is the globe.
Okay.
This is somewhere in America.
Okay.
If I set
so where's down? Show down on that.
Down is here.
No, show down on that drawing.
On this drawing?
Yeah, just what, like right now, you point down right now in your room. Okay. Now you're in America, and let's just say you are at that level that you were just talking about, the one in America. Go ahead, point your marker up there at that. Where's down?
Down toward either the center of the Earth or down this way.
No. There's only one down.
to the center.
Down. Good. That's down. Now talk about the level at the North Pole.
Up here. So
Where's his down?
this way.
Yeah. Now the South Pole.
Same way.
That's correct.
So what you're saying is
Wherever you are, you can point down. And if you're standing, it's at your feet. You just point at your feet. That's down.
right. But level is not a straight flat line. Level is
That's correct. Level is not a flat line. That's correct. Think of it this way. Think about the old transit with the level vial, right? That bubble in that piece of glass, when you tilt that glass, you can tilt it until the bubble is evenly centered in the level vial, right? Because the level vial is curved. You realize that, right?
Yeah, most are.
Well, they have to be. If it's flat, you could never. If it was an absolute straight piece of glass, it wouldn't work. But the level vial is about maybe an inch long, but it has a radius of, I don't know, it's a pretty big radius, so that there's a very slight curve in that piece of glass. And on the glass are etched usually 20-minute or 20-second demarcations. And the level bubble inside there is probably about a 1/4 inch long. It's pretty small. And as you turn the screws of the instrument, you're orienting that piece of glass so that that bubble will rise to the top of that level vial. And I don't know if it'd be worth us showing a picture of that or not, but you get the idea is that something is pulling or forcing that bubble to where it centers in the center of that level vial. And when you've done that, you've established the instrument to be perpendicular, right? The base of the instrument, the horizontal axis is now perpendicular to the direction of the vertical, right? And when you look through the scope, you're looking perpendicular to the down direction, right? That makes sense, right?
Right. So you'd be looking like this.
You would be. Absolutely. Yeah, exactly. Of course, it's an exaggerated sketch you have there. Of course,
Right.
It's very slight. However, the manual for your leveling indicates how far you can possibly go before the curvature starts to affect your readings. And you certainly are well versed in the fact that you're taking balanced back sights and foresights, right? If you didn't, what would happen?
I have taken unbalanced shots.
Right, I'm saying if you take a lot of unbalanced shots, like if you purposely took 50-foot back sight, 200-foot foresight, and then you go up ahead, 50-foot back sight, 200-foot foresight. If you do that for a mile, you're going to have a measurable difference that you would not have if you were taking balanced sights, right?
No, I've done that.
I'd have to see that data because I know you will accumulate, you're going to accumulate error.
And that's the next leg that we do out in Salt Lake. That's exactly how I'm going to do it.
Okay, so you're going to take very short back, yeah, but you're rocking the rod and your first level loop misclosed by what, 2/100ths of a foot?
Yeah.
You've already exceeded third order leveling. So I would really recommend getting a digital level so that you're a digital level and a rod with a level vial on the rod so that you're just holding it plumb. So you could do some high order, second order leveling, that type of thing. In Missouri, when you guys did highway surveys, did they have a manual that talked about orders of accuracy?
No. No, in I guess regular plane surveying, you're allowed 1/100th of a foot per turn.
I don't think so. 100th of a foot in error per turn.
Per turn.
I'd like you have to show me that, because I know even Missouri right now has a really good website for their DOT. Do you have a link or a manual we can go look at where you're allowed 1/8 of an inch? That's an eighth of it. An eighth of an inch is 100th of a foot.
Yeah, that's not for DOT work though. For
Well,
DOT work, no, you're going to run first and second order work. I'm talking just regular plain surveying for construction work.
oh, for construction, you're not really running levels. You're just setting up a level and working off of some control on site, and
Right. Yeah, I'm not talking first, second, third order work.
right. And in that case, so you're going to be leveling much tighter. And with the work you're doing there in Utah, you're going really far. So 100th of a foot per turn, you'd have a lot of slop. So you want to control that.
I don't accept that. In my world, I don't accept that. In my world, I want to hit flat or within 100th in a loop.
Okay. So, okay. So yeah, I'm still trying to wrap my head around the fact that you know how to do this work, and you're still convinced the earth is flat, and it's because of leveling. Is that what did that?
No, that was one of the first things that popped into my mind. And then I looked into it, and this is how it's explained. So I was like, well, and one of the experiments that we're going to be doing down there in Utah is going to be setting up to set up a laser to test whether this is true or whether this is true.
And how will you do that? Let's hear about that.
That's what we're doing now is we're running every 3/4 of a mile. We're putting in number 5 rebar, 18 inches long.
Okay.
To get an exact elevation on it. Then once we get that 7-mile stretch done, what I plan on doing is setting over a laser, getting a laser and putting it perfectly level.
How will you get it level?
How will I get it level?
Yeah.
With probably a 8 or 10 foot long carpenter's level.
Well, that level has a tolerance associated with it, and it's probably going to exceed. I mean, that level is designed for a certain purpose. You're going to try to make that laser level for a 7-mile shot?
No, not a 7-mile shot. Not even.
Okay.
Let me finish.
Oh, go ahead. Go ahead. Sorry.
Yeah, I'm not going to go 7 miles because you have too much beam divergence.
Okay.
So if I set up a laser and I level it up, our instruments that we level up, our bubble's only this long, isn't it?
Well, yeah, but which instrument are you talking about? The total station, a transit?
Well, nowadays we use a digital level.
Yeah.
For our data collector.
Yeah,
back in the old days, on most of your instruments and your transits, they have a level bubble that's about this long on either side.
Yeah, it's that long, but what's the sensitivity of the level? It's about a 20 arc second or better division per division. Remember that's a curved piece of glass.
So
it's small. That's true. It is small, but it's curved. And but go ahead. So you're going to set this up.
Set up a laser here. Then at 3/4 of a mile, set up a target, a whiteboard, anything that this laser will hit that we can see the beam on.
Okay.
Then, like at 3/4 of a mile, then go 1.5 miles to the next one. Set up a laser there at the exact same elevation and level, the the exact same elevation here, point these lasers at the target. One 1.5 miles and one 3/4 of a mile. Now, if these beams converge at the exact same spot, this is level, this is not.
Well, again, you've got to, how, we're back to the question of leveling the level or leveling the laser. If I were you, are you going to get that one that they're using out there over there at Lake Balatron in Hungary? Is that the laser that you're going to be getting?
No, I think Jaren's going to use that, but I may see if they would let me use it for this.
Okay. Whatever laser you get, I would encourage you to get the same type of tilt sensor that is inside the S6, your robot, your total station. It's the same type of tilt sensor that they use on machine-controlled construction equipment, the same type of tilt sensor that's used in horizontal directional drill boring. These things are very, very precise, like better than a second, right? They're very, very precise. And that's the only way you're going to be able to say that the laser has been leveled. You know, you need some precision there, I think.
Right. Yeah, I'll take that into consideration.
Otherwise, you're just using carpenter's level, which is only good for, you know, putting a door in or making sure a window is level, or, you know, if you're doing some block work, it's only going to work in that general location, right? You can't, I know I said 7 miles, but you're not going to be able to go 500 feet without that tilt affecting the direction of that laser.
Yeah, well, I'm sure it's going to be trial and error.
Yeah. So so you're using a Trimble S5, you said?
Yeah, that's what I use.
Okay. What is that, a 3-second instrument?
No, I think it might be 3.
3 seconds. So it's got some precision on it. That's a nice instrument. I think that's a nice instrument. Have you ever set the instrument up when you're traversing? Oh, let's talk about traversing. So when you do any traversing, what kind of sight lengths are you measuring? Like about
nowadays?
Yeah.
Oh, probably less than 400 or 500 feet.
Okay. That's because of the radio issue that you're having?
Yes.
Okay. You can get around that too if you can put your targets out further and just have the data collector near the instrument.
Right. If I want to set up a target a half mile away, I could go set up just a stationary target, then walk back to the gun and then shoot it from there right next to the gun.
Yeah, I would encourage you to try this. What you're doing here with the leveling and the laser is fine. I mean, that's a good test. But I'm also encouraging surveyors to look at their zenith angles.
That's one of the other things that I'm going to do when I'm out here.
Okay, let's hear it.
Is do the same thing. Set like the experiment that you done, I believe, what was it, across the Copper River?
Well, I've done a few. I've done them across water, and I've done them on land.
But the same thing, set up a target down here, set up the instrument here, shoot the target knowing the exact elevations, the exact distance, record the zenith angle, flop, and do the same thing.
Yeah, you should take probably in those lengths, you're going to be wanting to do maybe six repetitions, and you're going to want to do them quickly. Like get one done, boom, get in the truck, go up, switch. So you want them to be near what's called near real-time reciprocal zenith angles. Now, also, you're going to have to really watch the atmosphere. And you've got to take temperature and pressure readings because, you know, there is refraction. And so the further out you go, the more that refraction will affect your results. I've tried to do the tests less than. So What kind of line lengths are you going to be trying to do that on?
Oh, I'm probably going to start off at like maybe 3/4 of a mile and then see what I get, stretch it out. Because
Yeah.
once you get too far, even I used to take mile shots breaking down sections, and you get the target looking like a snake
Yeah, obviously you can't sight on it.
waves.
Yeah.
And I used to, you'd have young people that'd get behind there, and we'd go do our calibrations on it. It'd be off 3 or 4 tenths. There's an art to it. And that's what I used to tell them when you had the double crosshairs that you were looking through.
Yeah.
Through the transit.
Yeah.
You'd have to get that pole and you have to center, you have to watch it for a few minutes and try and get the center of the waves to get an accurate line on it.
Yeah, that's how it was when we were trying to go real far, and now we're using GPS, and we don't really need to do that anymore. But for these types of tests, yeah, we do want to do some longer lines. 3/4 of a mile is good. I would suggest that you try 1,000 feet. 1,000 feet, that 3-second instrument should be able to detect the inclination of the plumb lines between the 2 points. And it's there. You're going to measure it. I don't know what else to tell you except that you will discover that your plumb lines are inclined to one another. They are not parallel. And yeah, so if your scenario there, the straight line were true, all the plumb lines would be parallel. Is that true?
Yeah.
Yeah, but they aren't. And you're going to find that out when you start measuring reciprocal zenith angles along a traverse. And when you go for that whole 7 miles, that's what you're going to have across the entire thing. I mean, I'm not trying to predict it. I'm just saying that's what I've found. And I think you'll find the same thing. So when you do this, are you going to make your raw data available for people to look at?
Yeah.
Oh, good.
I wouldn't hide anything.
Excellent. Well, I get that from you. And I'm glad to be talking to you because this is good. I think you've got the skill set. You do have the ability. You've got the experience. So far, I haven't seen anyone else out there. And every time I see someone like you or George Hadnack, if I'm pronouncing his name correctly, of course, George is not a flat earther. He's an engineer who's doing these tests on that frozen lake up in, I think it's Minnesota. He's, and I'm going to put the link to his channel and everything in this, once this is done and up on the web, so people can go see what he's doing.
Yeah, no, I've got a lot of experience at doing long half-mile, 3/4 miles. One with that little company that I first started working for when I moved back here to Colorado, we went out and done a big aerial job for Highway 36 that runs from Denver to Boulder.
Mm-hmm.
And
I've done the same thing. I've got pipeline jobs that go for 300 miles. I've created low distortion mapping projections for 700-mile long jobs that cross several states. We should probably talk about that, like state plane coordinates, why they are there, why do surveyors use them. In the situation I just described, when you start crossing state lines, you're not able to use any one state's state plane coordinate system anymore. So you've got to do something about that. A lot of times people use UTM, but what's your familiarity with mapping projections for these long projects?
Oh, just before we jump into that, I was going to finish the deal I was talking about on the 36 highway job. What we did is we went out and we did horizontal and vertical trigging. We trigged 3/4 mile. I don't think we had anything under a half mile. And we traversed and trigged all our elevations and then set up with GPS. And whenever I did my vertical, it was just 2 angles. Forward, flip the vernier, spin it around, read it again. And all that, the traverse and all the vertical in that entire job was all within 300s, vertically and horizontally, without any refraction corrections.
That was a loop?
It was actually a big, long traverse.
Yeah, I mean, a loop traverse.
No, actually, it was an open end traverse.
Yeah.
And we set up on it with GPS, calibrated it, and went around and double checked all the stuff. Because when we did it, we didn't have GPS. We acquired the GPS like a month later. Went back out and checked all that, and everything vertically and horizontally was within hundreds.
Yeah, that's a testament to how well this equipment does work. I know Jaron was interested to hear, how does GPS compare to non-GPS equipment like what you were just describing? I agree with you. We get very good comparisons, don't we? Yeah.
Yes, and it's gotten better over the past 4 or 5 years with GLONASS.
Yeah, that's the whole thing. I mean, in the early days, we were just doing static occupations. And for the people listening, they'll know what we're talking about. You would have to set these receivers, these GPS antennas over points and let them sit there, sometimes for hours and hours. The constellation was sparse. Back in the late 80s, early 90s, there were not many satellites up there, and you had to plan accordingly. You had to look for when you were going to have 5 or more satellites available and plan your survey to occur at those times. And you would set up, well, I've worked on campaigns where we had 9 and 11 receivers all set up across the state doing large geodetic campaigns. And you collected all that raw data. These are just radio signals that are being counted in a way. I'm just kind of giving you a very simple explanation, but that raw data had to be processed to compute the vectors, the 3D vectors between all the points. Well, the next thing that happened was they figured out how to do that same thing in real time, and it's known as real-time kinematic, or RTK. And the way that was done is that you put a radio at the base unit, you set the base receiver over a known point, and then you broadcast those raw observables out over a radio signal. And the roving, the one that you were at, where you were working, you are receiving the radio signal from the base. And then your rover would combine the observables coming from the base unit. This is very high tech. I might be going in over people's heads, but you're basically solving for the vector in real time, and that's called RTK. And we've done that for decades. And then the next variation of this, or the next step, was, hey, instead of putting a radio at the base, let's just broadcast this data across the internet. And that's called real-time network, or RTN. And all the different manufacturers have their own version. And the one that maybe Chris is familiar with, that I'm familiar with, is called VRS, Virtual Reference Station. And that is where your roving receiver jumps, you get onto the internet to get a live data stream from the internet, and you're getting your positions there. Now, all these techniques I just described all result in the same types of precision. Very, very tight. Yeah.
I'll step in and say that I do have issues with the VRS accuracy. I find it to be very sporadic. I've set up my transit, and just today actually we went and broke down a block with VRS with long occupations on the control point, set up my transit, and found 0.2 of error
in the vertical.
VRS.
In the vertical.
No, horizontally and vertically.
Well, you're in Colorado.
I've found a 1/2 foot in some of my VRS. I've screamed
Chris,
from the mountain. I've screamed from the mountaintops that the only way to be extremely accurate is to set up a base unit.
Yeah, Chris, let's get back to the state plane coordinate situation. I think you're comparing, this is the thing that happens often when people are not sure of what they're getting from the GPS. If you're getting state plane coordinates and you are in Colorado, you have a very large grid to ground scale factor going on, right? So when you measure the distance between two GPS points, right, you have a much, your measured distance is longer. Am I right?
Not if I do a 1-point calibration in GPS.
Oh, well, yeah, if you do a 1-point calibration, now you're going to slide your the whole situation to that point. Now,
in a 1-point calibration, that's actual ground coordinates or ground measurements.
For some duration, yeah, for a limited extent, you're correct.
We're talking city block.
Yeah, yeah. So, okay, so you are correcting for that. That's good. So you know what you're doing. I think, now out there in Utah, what kinds of GPS occupations are you going to do out there? Just collecting static data, or I doubt there's like VRS out there, right?
Yeah, I doubt there is. The only access I have to VRS, I guess I'll explain that kind of what I think it'd be for a little more layman's explanation or somebody that hasn't done it. Basically, what VRS is you have your MiFi box. Like you have, if you want to get on the internet with your iPad.
Exactly.
Or you want to get on the internet when you don't have Wi-Fi and you're on the open road, you have a little MiFi box and you dial into the internet. And once we dial into the internet, my GPS unit there's Coors stations, which are permanent GPS units that are set up over exact latitude, longitude, and elevations. They broadcast through the internet and then give us the information real time to our survey antenna or GPS unit.
That's good. That was a good explanation. I was going to pull up the Colorado VRS. Maybe we could show people.
Yeah, now here in Colorado, we have 3 different zones. We have north, south, and central for the WGS 84. We have 3 zones in Colorado.
Yeah, do you know why they need to break up the state into 3 different zones? Why not just one zone?
Well, yeah, I have a lot of questions directed in that direction.
Okay. Okay, so it looks like Colorado is just covered by Trimble's VRS now. Wonder why. Are you using the Trimble's VRS now, or are you using some other system?
No, I believe it's the Trimble VRS
Okay.
now.
There's a lot of DOTs set up their own, their own systems.
Right. If you knew their channel that they were broadcasting on, you could just jump right in on their network. But not with VRS, you'd have to have a radio. See, and I don't know, did you guys ever have the old 35-watt brick radio that used to mount onto your pole before they had the MiFi boxes?
Yeah, when you were doing just RTK.
Right, the RTK with VRS.
Well, if you're doing VRS, you're just hitting the internet, so you wouldn't need
well, I forget what the system was called. It was almost like VRS, but you had a little 35-watt brick radio that mounted onto your pole, and you didn't need a base. You just dialed in whatever the frequency was for the Coors station.
Okay, yes.
Right into the Coors. Now that system was spectacular.
Yeah, that is where you, instead of the base broadcasting to you, your radio is beaming back to a base someplace. Yeah, I'm familiar with that. So that works too. Now, that's a single base solution. I still think we're probably getting into things beyond what people are going to be able to decipher what we're talking about. Well, let's see. If you said you wanted to ask some questions about what you have going on the whiteboard in the back there, or you had some questions about state plane coordinates, I think.
Yeah, we could go into the WGS84. I guess give me your explanation of why they break it up into 3 zones.
Okay. For that, maybe I should share my screen, or I'll talk about your whiteboard there. No, you know what? Let me share my screen and then start. Let's see. Okay, I've got something here I can talk about. I've got the Utah project that we can talk about. And I'll bring up Google Earth. Here we go. Now I will share my screen.
While you're kicking it, have you used the R10 yet?
Yeah, I've been using the R10 pretty much since it came out. Now,
is it true that it knows where level is? You can just lean it over and take a shot?
Yeah, it has a tilt sensor built in. That's the kind of tilt sensor you're going to want to get an OEM of some kind of a tilt sensor that you can mount on the laser that you're going to use. It says that I am sharing my screen.
I see it on mine.
So you see my screen?
Yeah.
Okay, cool. All right, let's see. So let's talk about state plane coordinates. I have something I can show us. So here's the 3 zones in Colorado, as you said. You've got South Zone, Central, and North. You see that okay?
Yes.
Okay. I'll show you a state that just has 1 zone, like New Jersey. Well, there's 1 zone. That's a transverse Mercator projection because we're more north and south. Pennsylvania has 2 zones. They're Lambert zones, Lambert projections. Now, North Carolina is a 1 zone now. And the reason I wanted to show you this was that there was a time when they also had 2 zones, and that was back when we were on the North American datum of 1927. When NAD 83 was about to be published in 1986, some of the states that had multiple zones chose to just go to a single zone. Now, when you do that, you're going to have greater distortion, but they chose to do that. That's their decision. Now, over here in Colorado, I mean, that's a much bigger state. And also you're dealing with higher elevation. And so if Colorado, here's Colorado right here, big rectangle.
Yeah, big open box.
Now, if they had did the same thing as North Carolina did and went to a single zone, you would have huge scale factor working here or here. Let's say if you went with a Lambert conical projection, and let's back up a little bit. What are we talking about when we're talking about state plane coordinates? And I've done some videos on this. People can look at it, and people can just research state plane coordinates themselves. What are we talking about? We are talking about taking a curved surface of the globe and rolling it out onto a mapping projection so that you can use, instead of using latitude and longitude, you can use grid coordinates, northings and eastings, X and Y coordinates. And that's what that was what drove, or what the reason for creating the state plane coordinates, why it came about was, in fact, it was North Carolina that asked for it back in I think it was in the 30s, because of the fact that, they were creating long highways, and they're the ones who asked for an easy way to do surveying when you're going very, very long distances, hundreds of miles. And that's all these red lines that you're seeing here are the state plane coordinate zones for each of these states.
So that's interesting. They got Iowa and most of Minnesota in all one zone. But wait, no, that's broke up into two.
Yeah, they have a north and a south. And
Nebraska's all one, ain't it?
I keep doing that. Looks like Montana, they went to a single zone. How about that? Boom. Deal with it. They're like, hey, we're going to deal with that scale factor. And
Yeah,
so when we talk about scale factor, what we're talking about is the fact that when you measure a distance on the surface of the Earth, depending on what elevation where you are, you're going to, in order to come up with state plane coordinates, all of those distances at all of those different elevations have to all be reduced to a common surface. And back in the old days, before WGS 84, we were using the Clark spheroid of 1866 here in North America, and the distances were reduced to sea level. So sea level became the common surface that all distances would be reduced to. And then from there, you would project it to this mapping plane, or a mapping projection, to kind of flatten it out. I think I could find a picture of that. Let me get... Here we go. There's my browser. If we just look up state plane coordinates. This is the same thing that I'm showing you in Google Earth. Back here, go to images. Yeah, here we go. This is a good diagram. You've seen these, right, Chris?
yes.
And it's, it's very exaggerated. You don't see this, but it's exaggerated just to show you all in one little picture how, you could be measuring here, or if you're measuring up here, because the plumb line is inclined, you're going to have this distance will not match a distance over here. You're going to have all varying lengths throughout here. And so you won't be able to close a survey. You're going to have error. So what we do is reduce them all to one surface. Basically, it's like homogenizing all the distances. And then we want to get it off of a curve. We want to put it on a grid plane of projection. That's well worded. Grid, that's the grid surface. And this is where the coordinates are being computed on. And here, I'll show you the one in Utah.
Now, when you were talking about projecting that down, the plumb line is different than the pull of gravity, correct?
No, the plumb line is being pulled by gravity.
Well, I've read that's why the geoid and the ellipsoid don't have the same center.
Yeah, you're talking about the deflection of the vertical. I'll show you that. But before I go there, hold that thought for 1 second. I wanted to show people this right here. This is just one project I'm working on. This is going so slow. All right, so can you see this okay? I know it's grayed out, but
Yeah, I can see that.
so this one here, this is Utah Central Zone. And when you look at it, what they do is they pick an origin of latitude and longitude. This is 3820, 11130 is the origin. And at that latitude and longitude, they assign a false northing and a false easting. In other words, a very large grid value. And that way you'll never run into negative coordinates. As you go west, you're gonna still stay in positive coordinates. And this is a Lambert zone, so there are two parallels of latitude, 4039 and 3901. And that is how every one of these state plane coordinate systems are projected from the ellipsoid to a grid mapping surface. Just a quick explanation on that. And now let's go back to what you were saying. You're talking about I know there's some good diagrams for this.
Yeah, I think I've got one here on my computer. I'm trying to find it real quick.
Here's one. So, so the plumb line is what your level vial is set perpendicular to. And the ellipsoid normal is exactly that. It's a line that's normal to the ellipsoid surface. The difference between them is called the deflection of the vertical. And what's your question about that?
Okay, so the geoid, or I guess my first question would be the ellipsoid. Now, is the ellipsoid the distance from the center mass of the Earth to the surface? Or is the ellipsoid defined distance from the center?
I'm listening to you, but I'm not getting your question. Can you try it again?
The ellipsoid height. How do you
Oh, the ellipsoid height.
Yeah.
I thought you said the ellipsoid. Okay, I missed that word.
Yeah, the ellipsoid is the very center point of the mass of the Earth, correct?
The the ellipsoid, the WGS84 ellipsoid, the center of that is the mass center of the Earth, correct?
Okay. Now the ellipsoid height, how is it defined?
That's the height from whatever object you're talking about to the surface of the ellipsoid.
Is that a defined constant?
No.
It's forever changing. Depending
Yeah.
on the height of your antenna.
Yeah, that's right. If you take your GPS receiver, flip open the screen that has position on it, set it to WGS84, and raise it above your head, you'll see the ellipsoid height changing. Bring it back down, the ellipsoid height is going to change. So it's a vertical dimension. It's almost like an elevation, but the difference between elevation and ellipsoid height is the ellipsoid height is measured from the surface of the ellipsoid.
And yeah,
whereas Whereas an elevation is measured from the vertical datum surface, which approximates, for the layman, mean sea level. NAVD 88, our current vertical datum, is not sea level. It's not related to sea level. You can get a relationship between NAVD 88 and sea level, but you have to use tide stations for that. But I'm kind of going away from where you're going. Go ahead, back to what you were saying.
So now the geoid is based off of, it used to be mean sea level, but now I think they're going away from that, and they picked one benchmark and decided to call that sea level, which they have. So basically, the geoid is based off of their sea level benchmark.
No,
different than the ellipsoid.
No, you're mixing up several things. So let's pull that apart. The geoid is what you were just describing sounded to me like NAVD 88.
Yeah.
Yeah, that's
in before 88, they used an average of the 26 tidal stations to come up with their mean sea level.
That's correct.
And doing that, when they come up with the 88 datum, they found out that the sea level on the East Coast was approximately 3.5 feet lower than the sea level on the West Coast.
Yeah, they definitely not only from East Coast to West Coast, but they also, here, I'll use this one. When they did the tide stations on the East Coast you're talking about NGVD 29.
Yes.
Yeah, all of those sea levels were different, and all of these were different. And for NGVD 29, they just all said, okay, those are 0. And they set that to be mean. They call that mean sea level. Now, when they did the adjustment for NAVD 88, North American Vertical Datum of 88, the station that they held was up in Canada on the St. Lawrence River called Farthers Point.
Farthers Point.
And they held that as sea level, or they held that elevation fixed and then adjusted the entire level network.
Right. And I talked had a conversation with my boss. I was like, you'd think they would have done that to begin with. Picked one elevation and stuck with it.
And, the next, well, it's a presentation. I don't need that. The next datum that's coming, right?
Yeah, 2020.
Yeah, 20.
That's where they're developing or coming. They've been working on it for the past 7 or 8 years. The dynamic heights.
Well, they've always had the dynamic heights, but this new datum is going to be a gravimetric datum, and it's going to be interesting. See what they come up with.
I thought the dynamic heights come up when they were doing the Great Lakes datum. This when they started bringing in the dynamic heights because they were trying to figure out how the water was flowing in and out of the Great Lakes.
Yeah, it comes into play there for sure, and you will see dynamic height listed on any NGS point. You're going to see dynamic height is on there. So, yeah. But while we're interested in this might be a good one to talk about it. Why does that keep happening? I want to see that picture. Oh, do you see this picture?
Yeah.
I clicked on it because I thought, it'll be bigger.
Yeah, I've got that exact same one. I've looked at that.
Yeah, I mean, I find this to be true and accurate? Is this something you are suspect of and think is not valid?
Well, no. Let's kind of divert back to the ellipsoid height, because I think we were headed down the right road. So when I set up my GPS unit and I turn it on and I look at the position in WGS 84, it'll give me my ellipsoid height.
Yeah, that's H right here, small h.
Now that's calculated from the satellites, triangulating from the satellites. It comes into my antenna and it creates that ellipsoid height from the specific geoid model that I have loaded in, correct?
No, no, Chris, the geoid model has nothing to do with the ellipsoid height.
The geoid model just gives, and the geoid model versus the ellipsoid just gives me my separation between the two.
Correct. Without the geoid model involved, there's the geoid right here. If you do not have this separation, you're going to get an ellipsoid height. And that's true. And you can repeat that all day long and you will see that that's what you'll have. Now, if you want to relate this point to get an elevation, what we call an orthometric height, you have to know what's the distance from the ellipsoid
to the geoid,
to the vertical datum. Yeah. And the geoid model gives you that.
Right. So you have to have two of those figures. Either you have to have if you have the orthometric height and the ellipsoid height, then you can figure out then you could figure out to the geoid.
Yeah, you can. That's true. If you have if you know what the elevation is and you develop an ellipsoid height on that point, you then can compute the difference,
which would give you your geoid.
Yes, and
so over the years, isn't that what they've been using to adjust the geoid model to make it more correct?
Yeah, I mean, the very first geoid model I ever used was I think it was called OSU 90, came out of Ohio State. And it was crude. It was only gridded the grid was very sparse. So we've been through many iterations of geoid models going from, the 90s, geoid 93, 96, geoid 99. There was geoid 03, that was 2003, geoid 06, 09. We're now at geoid 12B.
Right, 12A and B.
Yeah, and what I've noticed, of course, over here on the East Coast, especially in New Jersey, New York, all these places where we have a lot of saturation of leveling. When you look at the amount of leveling over here, this is not a very good picture, but there's so much leveling and there's so many GPS observations on benchmarks. Our geoid model hasn't changed much through that time period, but for those areas way out in the mountainous areas and places where they've done more surveying work to compare GPS to the geoid model, they've been able to refine it and improve it. So that's why that thing comes out pretty much, seems to be like on a 3-year basis, 3-year period.
Yeah, except for this next one, it's going to be a little while.
Yeah, but the next one, like I said, is it's going to be a whole different thing.
But yeah, well, then I've got that right in my mind. If you have you got your orthometric height that you determine by differential leveling, and you set up your GPS unit, which then gives you your ellipsoid height.
Yes.
Then you use that to refine the geoid model to better match the ellipsoid and the orthometric.
Yeah, and it sounds to me like you're actually just talking about doing a refined geoid model in your area, because you can take the geoid model as it is and do some improving for your local area. That's true.
Yeah, because I think NGS every year has one day where they ask people if they have a GPS unit to set up.
That's coming up. Yeah, that's coming up.
and then send it into them.
Yep, it's coming up in March. It's Surveyors Week, and they want surveyors to get out there and occupy benchmarks.
So how is the ellipsoid determined from GPS?
How is the ellipsoid determined from GPS? I'm thinking where to go with that one. Because of course,
software?
Well, hang on. You realize, of course, that we've had spheroids before WGS84, right?
Yeah. I
For
forget the name of it. I think most of the earlier GPS units were loaded with 95. I forget the exact name of it.
No, I'm saying before GPS.
Because one of the explanations that I read about the ellipsoid height is that the satellites can only determine the center mass of the Earth. And then when you set up your GPS unit, then it triangulates and gives you your ellipsoid height. But it has to be some sort of determined distance or software that gives you your ellipsoid height. Or otherwise, you'd be able to set up with your GPS unit and be able to triangulate your orthometric heights from the satellites without having to run differential leveling.
Here's how it works, Chris. Of course, the ellipsoid is a model, right? So,
right.
And as a model, it is not something you can physically measure. Whereas the geoid is measurable, right? That right there, that geoid is a measurable thing. And every time you set up your instrument and level it, you are aligning that instrument to the direction perpendicular to the geoid.
Right. And but what determines the geoid height?
Well, hang on. I'm trying to answer your first question. Back here, I'm distinguishing this from this, the ellipsoid. So
right. Sometimes they cross over.
Yeah, well, for the United States, for the coterminous United States, the geoid's below the ellipsoid.
Right, until you get way further north.
You get up into Alaska, they definitely switch. So it undulates. The geoid undulates in reference to the ellipsoid. In a way, you could look at the ellipsoid as being a least squares best fit of the geoid of the whole Earth. Does that make sense to you?
Yeah.
Okay, so now let me go back to this. I'll try to find a good picture for you.
Yeah, we probably lost all the layman's an hour ago.
Well, here we go. Cool. This is perfect. Nice. So GPS satellites are, oh, by the way, you're using GPS. You think the Earth is flat. Are there GPS satellites?
No, not in my world. We triangulate off radio towers and cell towers.
And what did you do to verify that? Or is that just a belief?
Oh, to verify that we triangulate off of cell sites instead of satellites?
Yeah.
Well, part of it is what I'm trying to get at here on pinning down where the how the ellipsoid's done.
Well, I'm going to show you that in a second, but
let me back up a minute. We do quite a few cell sites. We go out and locate and give exact latitude and longitude and exact heights of all the antennas and turn that over to the cell companies. Then with that information, you could definitely turn that into a triangulation point. Do you agree with that?
A triangulation using what?
If they had an exact latitude and longitude.
No, no, I understand. Listen, I know this upwards, backwards, forwards, and sideways. I'm asking you, how do you use it as a triangulation point? What means are being used to triangulate from a cell tower? With a theodolite?
No, they
With broadcast what?
They broadcast a signal from
What
that
signal?
cell site.
What signal?
You pick up a signal in your Wi-Fi box. You pick up a signal.
Wi-Fi, Wi-Fi is what? What frequency?
Right off the top of my head, I don't know.
Right.
But
Well, let me. We're going to drill down on this.
hang on, before we go in.
No. I want to drill down on this, Chris. This whole thing about GPS coming from cell towers. You know, if you wanted to, okay, I won't go there. What frequencies are being broadcast from cell towers?
Hang on, they broadcast a GPS signal from cell towers.
Yeah, what frequency, Chris? What frequency?
L1 and L2. They broadcast.
They do not. That is, you mean, like, where did you ever come up with that?
I've been through walkthroughs, and walkthroughs are when they go into a building that does not have cell antennas on the roof. When they go through a walkthrough, the first thing that they do is they bring in a GPS signal from fiber optics. When they put up a cell tower, and you can double check me on this, when they put up a cell tower, they pair the GPS signal and the cell signals both together. They pipe in a GPS signal into every cell tower. I've been.
Oh my God, Chris, you have it backwards, dude. They are using the time signal from GPS to synchronize the cellular network. You have it utterly, absolutely backwards. All right, so you can check me on that, okay? And here, this whole thing about GPS, this whole thing about GPS coming from cell towers. What am I trying to find here? Come on, Jesus. It's just it makes me irate a little bit, but that's okay. Let me show you something, and I'm going to put this in the link. How do I find my own freaking channel here? I'll put this in the link, but I just want to make people aware who are watching. If you really want to know what's going on with GPS, and if you want to see a test that you can do yourself, go and watch my little video. It's one I did way back. I think I passed it.
Yeah, I've been with the engineers through all the wiring and everything.
Yeah, Chris, no, if you can't answer me the actual frequency and so forth, here, come on, just one sec, just hold on 1 second here. There it is. Everybody can watch this. Video is going to be about GPS. I'm not going to go through the whole thing, but you can watch it. Anybody can do this. I went and did GPS in areas where there is absolutely zero cell signal. So don't talk about GPS coming from cell towers. The other thing I want to tell you, Chris, is that you can look at the raw data. And in the raw data in your GPS are the locations of the transmitters. And guess where they are? I'll show you where they are.
Oh, you mean like when I dial into VRS, it'll give me, I've looked up the base.
No, Chris. I'm talking about the raw data, not VRS. That's a radio broadcast across the internet. You're going to need to, I think it'd be great if you dig in a little deeper and learn a little bit more about the technology you're using before you come to some of these conclusions. But I'm going to explain how this works now. The raw data has that location. This is the transmitter. The transmitter is a satellite. It orbits the Earth. And what that means is it falls around the Earth, and it does it twice a day. That's the speed it's moving. It falls around the mass center of the Earth. Okay? And it is broadcasting. It used to be just L1 and L2. Now there's L5 and there's more. There's also more than GPS. We have Russian GLONASS. We have European Galileo and others. India is involved, Japan, China. And these satellites fall around the mass center of the Earth, and they are broadcasting their own position all the time. So you can really think of them as like a monument or like a control point that is a radio station broadcasting which satellite it is and its position.
Right. Basically, they kind of work like a clock. It sends a beam to my base unit or my rover, and it's hitting 7 or 8 or 9 or 10 satellites, and it's triangulating its position between all those. And it basically works as a clock. It times how far it gets from that satellite to my antenna.
And so it's actually trilateration. It's distance measurements. Let's see if there's a nice diagram of that. Here, yeah. Here's the person on Earth. This is a compressed picture, darn it. But yeah, I mean, if you want to say triangulation for people just wanting to visualize it, let's try this one.
Yeah, I'm just trying to make it so.
Yeah, so here you're on Earth. This is one satellite. Of course, like you said, Chris, you're going to be receiving from several. You need at least 5 if you're moving. Generally, nowadays we have way more than 5.
Yeah, I work off of 10 or 13 on a daily basis.
Yeah, so you've got Russian satellites involved. You're using GLONASS, and that's how your position is determined on Earth. And it's done not in latitude and longitude. It's done in Earth-centered, Earth-fixed Cartesian coordinates that are then converted to latitude and longitude. And then from latitude and longitude, we project those onto mapping planes like this.
Makes up the geoid model that we work off of.
Well, the geoid model has nothing to do with what we just went through for the last minute or so. The geoid model comes into play when you want an elevation, not an ellipsoid height. Oh, here's a cool picture. And if you didn't know it, the GPS satellites also have GPS receivers on board. And so they are positioning themselves relative to one another as well. That's just another feature of what's going on.
So let's go back to that last thing that you were just talking about. This satellite projects the center mass of the Earth to
No. The satellite is falling around the mass center of the Earth.
And it knows its exact position to the center mass of the Earth.
Yes. Yeah, the Earth-centered, Earth-fixed coordinate system, ECEF. Gonna get big for me or what? Yeah, so these satellites are falling around the Earth, orbiting the Earth. Its XYZ position is known continuously. I mean, there's more technical explanation of that. The Keplerian orbital parameters are what allow us to compute the XYZ. And that it comes to you in a broadcast ephemeris. The almanac and the ephemeris contain the navigation message so that your receiver can decode it, determine where the satellites are, and compute that pseudo-range position or that pseudo-range distance, which then gives you your position because you're going to do it from more than 4, maybe 5 satellites, and where they all intersect, is where you are. That's the position.
So it knows your exact position on the surface.
Yeah. That's how it works. And, there are forerunners to GPS. Before GPS, there was the Navy transit system, which was a Doppler satellite system. It took longer to do, but it was still a satellite-based navigation system.
Yeah, in the early days, they used LORAN.
Well, now LORAN is something else altogether. I mean, those are what people are trying to say GPS is now, and of course it's not. Where are we? Here we are. The LORAN. Well, let's look at that. I'm having a good time using Google. Yeah, LORAN is. Let's look at some images here. Those are ground broadcasters, and I'm not as well versed in LORAN in terms of what signals they are, but this is how it works. It's going to intersect these frequencies, and you're going to get your position. Very similar to the way they would be sighting with a sextant to lighthouses. So in this case, it's going to be an electronic navigation system. And so this same idea is being used with GPS, except for instead of them being on the ground, they are 20,000 kilometers or 12,000 miles above us, and they're moving. And you can see them moving on your screen. I mean, they're not stationary. You can bring up the plot on your data collector, and you can see that they are moving.
Right. You bring up the screen, and it shows you their exact degree off of the horizon, exact satellite that you're looking at.
Exactly.
The name of the satellite.
Yeah. So, there's LORAN, and then and now we have GPS. But I hope you look into it a little further. I hope that you continue with your test here, and you're gonna find out that the Earth is not flat. And it's not that hard to do. You could find it out tomorrow. You could take your total station out and measure 1,000 feet from both ends of the line, and you're going to instantly see that. Do it during conditions where refraction is minimal. Okay, and you could even say it's at its worst. To be conservative about it, but use a short distance. Like if I take my T2, which is a 1 arcsecond theodolite, and I can do this in 800 feet, and you have clear visibility. There's nothing shimmering. There's nothing moving. You could take 4 sets of angles, and you're gonna have a standard error of a second or 2, right?
Right.
So you could try it for yourself, and you'll see. What do I have here? You going to talk about this?
Yeah. One of my questions is too, is whenever we're working in state plane, we're working in plus or minus the scale factor, correct?
Well, it depends on where you are, but yeah, I see where you're going.
Colorado.
Yeah.
Actually, I think this is Utah. This is the Utah one.
Okay. Now that's scale factor just for the mapping projection. It has nothing to do with your difference in sea level, right?
Right.
There's an elevation factor as well.
Right, because all survey measurements are made flat and level. You don't use slope distance. You always use a flat and level measurement or horizontal measurement.
Oh, when you reduce it, sure. But you're measuring slope distances directly.
Correct. But when you come up with your horizontal distance, it's going to be a straight level measurement.
Well, it's going to be, that's the thing. Look, think about it. If you're at the top of a mountain and you measure a slope distance down to the bottom, right? Let's say it's a mile long and it's a several degrees slope. If you reduce that slope distance to a horizontal distance at the instrument station up on top of the mountain, you're going to get a value. Now, if you go down to the bottom and measure the slope distance up to the top, the slope distance is going to match very closely. But when you reduce it to the horizontal, that horizontal distance is going to be shorter than the one up at the top.
Right.
And because of that is why they developed the state plane coordinate system. That's why. And that's why we reduce distances to the horizontal. I mean, to sea level. I'm starting to get tired here. It's about 10:30. Had a long day. I want to show you. I'm going to come back to you in a second, but I want to show you something that you may not have seen. That is actually on this topic. I feel like I'm starting to lose it. I'm just tired.
I hear you. It was a long week for me too.
Oh yeah, it's Friday, right? We should be doing something else maybe. No, I'm enjoying talking to you.
Well, that's one of the reasons I wanted to talk to you is to clarify where I was wrong in interpreting geodetic surveying. And you've helped me out tremendously in a few areas like the ellipsoid and the geoid.
I can't even spell right now. Have you ever seen this book?
Yes, I actually have that.
I show this book to everybody. I like it a lot because it's short. I like the style of the writing. It's really old-fashioned. It's free. You can just download it.
Yeah, I already have it downloaded. I've actually read through quite a bit of it.
Yeah, and it really tells an interesting story of the
history of geodesy. Yeah.
Well, you could say it's the history of geodesy, but more to the point, they were very interested to know the shape of the Earth, and they really wanted to know what is the length of a degree. And I don't know. So you have this book. You should really read it and look at the sections where they discuss reducing the distances to sea level, which comes back to what you're talking about right now. Now I can come back to you. I wanted to kind of interject that book. And let me come back and find you. Where are you? There you are. So what I just described was, and you're right. I mean, you can't just use slope distances. You need to reduce those to a homogeneous surface. And what you'll find is when you're working in areas where the terrain range is great, you will not have homogeneous reductions of distance between the top of the mountain to the bottom of the mountain. And that's why in that book, they constantly are discussing the need to reduce their lengths to sea level because they're up in the mountains, then they're down in the plains, and they're back up in the mountains again. And they're going really, really far. I mean, they're going many, many hundreds and hundreds of miles doing that triangulation. And so there, I just wanted to interject that here. But go ahead with your point that you want to go through here. And also, I don't think anybody listening knows what these scale factors are. Do you want to describe what that is?
Yeah, I'll get into that here. It's more of a question. Okay, if you take the radius of the Earth and you calculate the difference between the arc length versus the chord length in 10 miles, no matter whether you're on a curved surface or whether you're on a flat plane surface, the difference is only 100.5 difference in 10 miles. So my question is, why do we take and squeeze everything down, kind of like down on this one? That's basically what you do, is you're scaling your distances down to your state plane coordinates using this scale factor, correct?
I'm still wondering if you're correct about that 100th. I'm not so sure about that.
Yeah, I guess double check me on it.
Okay, I will.
And I think I've even done it for 20 miles and it doesn't, I think it may be at 1200s. So my question is, if you can measure 10 miles and your chord and your arc is only a difference of that, why did we do this?
Well, have you read the manual on state plane and what they're doing in there? Because this thing that you've drawn up here, while it's an interesting question, and I will check that, I don't think that happens in reality because, again, you got to realize you have elevation involved here too, right? We are not on that blue circle. That arc there you have drawn there, we're not on that.
Right, we have undulating terrain.
Yeah.
But let's say
the difference, it's not a matter of the chord. It's a matter of the slope distance. You got to remember why we're doing this. They made state plane coordinates not because there's a very small difference between the chord and the arc length. That isn't it. It's the reality of us being on the ground, on the earth, from hill to valley, back up to hill again. And when you go across 10 miles like that, you are going to accumulate, large distortions, not hundredths. When you start reducing all those slope lengths, they're not going to reduce to the same surface. And that's why they made the state plane coordinate system, to get it onto, to basically flatten out. I'll go back to, well, you've seen that, like, the transverse Mercator projection is a cylinder.
right.
And the conical projection is the Lambert conical projection is a cone. And all that is a mathematical surface that you stick onto the globe, and or you insert the globe into the cylinder, project the features onto that mapping plane, and then cut it, slice it, and roll it out. And now you can just use plane geometry and trigonometry and X and Y coordinate values.
So when you set up a transit and you're just using a transit, not GPS, what's your scale factor?
You mean if I'm just measuring locally on the ground right where I am?
Right.
Well, there'd be none. But if I want to be...
It'd be a 1.0 scale factor, correct?
Yes. But if I want to be on state plane, I got to somehow orient myself to the grid. And if I don't have GPS, then I'm going to go look for a monument that has grid values and base my survey on that.
Right. But yeah, let's say you're you're not using let's say I fire up my GPS and I come over here and there's an NGS monument and I go 10 miles over here and shoot the NGS monument again.
A different one.
It really doesn't matter what's in between here. Let's say for the argument's sake, these two are the exact same orthometric height.
Sure.
So whatever's in between this and this really doesn't come into play, does it?
Correct.
So even if, and I think in 10 miles, you would have 66 foot in here.
Yeah, but it doesn't matter because, like you said,
right, exactly. Let's just forget I even said that. Yeah. But still, if we do this, what's between it doesn't matter. So again, why do we go down to?
Why do we do what?
Why do you scale those distances down?
Well, you know, when you put that GPS on the monument on the left, let's call it A. Put an A, write A up there. There's monument A. Another one's B. All right. So when you put your GPS receiver on monument A, you're going to get a latitude and a longitude there. All right. And you put it on B, and you'll get a latitude and a longitude there. And the difference between the latitudes and the longitudes is the arc. Right.
That was another one I was going to ask you.
So wait, follow my explanation here.
Okay.
I'm going to talk about this a second. Now, you know, on the curve chart everybody uses, that theta angle. You know which one I mean?
No, I'm not with you. Oh, yeah, okay, I know which one you're talking about now. Yes.
I wonder why these don't just pop up. That's so blurry. Okay, yeah, theta. Here, let's use this one. There, theta. So let's say this is point A on your drawing, and there's point B, or over here, exaggerate it.
Yeah, exaggerate it.
point B. So here's A, here's B. So with the GPS, you're going to get a latitude and longitude here, and you're going to get a latitude and a longitude here. Now, if you want to just play with this and roughly approximate this, theta, take those Latin longs and just convert them to decimal, and then take the difference in latitude, square it, take the difference in longitude and square that, add them together, and take the square root, and you'll roughly approximate that theta. That's the arc between the two latitudes and longitudes.
Right, and that's how I understand it is latitude and longitude is arc distances.
Correct. Okay, now where were you going with the fact that if they were on the same elevation or something? I'm not
sure. What I'm saying is the difference in the arc versus the chord is only 1/100th and a half.
Yeah, like I said, I'll have to check that. I don't have that in my head.
If you kick up, you could Google arc calculator.
Yeah, but again, my answer to you was that we are not on I'll go back to your screen, what you're showing. We're not on that blue circle. We are on this. And now you're talking about the difference. You're using GPS here, GPS there, and you're saying, well, we don't care about what's in between. Well, do we or don't we? If we don't care about what's in between, then we don't need the state plane coordinate system, do we?
No.
No. But if you care about running a roadway, from A to B. If you care about doing some type of construction from A to B, tunnels, railroad, some infrastructure, you're going to want to survey across all that terrain, right?
Right. So I think what you're getting at, let's say point B is on a mountaintop, point A is on the plains.
Yeah. And, you do have undulation, you have all kinds of terrain in between. You have to make your way through there. And so what you have to do is create a datum to work on. And it should be a common datum. And besides, it's not just the surveying that's happening, it's the engineering. The engineer has to design this infrastructure. And if he's going up hills, he's got to figure on that. And then he's got to figure on going back down the hills, for, let's say, a transportation corridor. All that has to be figured in. You've got all that topography that's got to be calculated. So I think a real good background for you, if you haven't read it, is the history of state plane coordinates. And it begins in North Carolina. I like to make this point. They're first in flight, and they're first in state plane coordinates. Woohoo. Inside surveyor joke, whatever. But I can be so corny, and it's getting late, so I'm going to embarrass myself tonight. Anyway, read that. You're going to see what their struggle was and why they needed to do it. There was obviously a need for it, or else we wouldn't be using it. And if you go and traverse, and I've done it, I have traversed 10, 15, 20 miles between geodetic monuments. And I can tell you that if you do not reduce your distances correctly, you will not close that traverse. You will not close it. And like I said, go back to this book. They talk about reducing their lengths to sea level throughout this book. It's an interesting story.
Do you still have the map up with zones in it?
Oh, I can bring that up. This one here in Google Earth, like this?
Yeah, that one there.
Yeah.
So another question I have is see the flat plains out to the east of Colorado?
Yeah.
And then you have the mountains. Why would they break those three zones up going over the top of the mountains instead of putting a zone in the flat areas? And
I'll do one here. I see what you mean. Like, why didn't they go north south?
Exactly.
I don't know who to.
Because that just brought up a question when you were talking about the high terrain. With the way they have those zones set up, you think they would have set up the mountains in their own zone and the plains in their own zone. That's
what it looks like New Mexico did.
Yeah.
So I don't know. You've got to call the state of Colorado and find out why they did that. Maybe it has to do with keeping certain localities within the same zone. I don't have an answer for you. It's a good question, but we see that other states did it differently.
Yeah. But yeah, Colorado and New Mexico kind of rear their ugly heads in the mountainous terrain. But it looks like New Mexico did what would seem to be the best way to do it if you had the high mountains versus the flat plains.
Hey, I wanted to show you this. I do want to get to this before we sign off. Hey, do you want to do this again sometime?
Yeah. I'll do a little reading and
yeah, do that. I'll be a little more prepared with things to discuss. This was a little rough tonight, but I really wanted to. This is like maybe our really second conversation, really.
Yeah, I think we talked on the phone for a half hour before this, and then email.
Where do I have? I've got another project to bring up.
Well, while you're looking for what you're doing,
Hey, do you have, sorry to cut you off. I wanted to find where you are. You had given me your latitude and longitude.
Oh, out in Salt Lake City?
Yeah, do you have it off on the top of your head, or should I try to find where I wrote that down?
Oh, I can get it for you. It is.
Here, I'll key it in right now.
Uh,
Hold on one sec. I'm going to put in, create a point. Chris. Go ahead.
you ready for the latitude, longitude?
Yes.
It's 4104 24.3 north.
Okay.
112 12 59.78 west. Yeah, I got a quick little survey story while you're doing that.
Looks like I already have you in here. Hold on a sec. Look at that. I'll say no. I guess I do have you in here. There you are. Oh, there you are. Okay. This is what I wanted to show you. If I send that to Google Earth. Yeah, go ahead. Tell your story.
Well, the story's about George Washington. He went out and did a survey, and the guy that he did the survey for was questioning his bill. And he told George Washington that he wanted his bill itemized. It was like $300 for the survey, and he was wondering why it was so expensive. So he broke it out. The rebar was, say, $10 for the rebar or whatever he used to set his property corners with. And the rest of the money was for having the knowledge to know where to put them.
I had heard that before. I hear jokes and forget them, but it's good because I can enjoy them all over again. That's a good one. Thanks for sharing that. I wanted to show you this. Like, this is where you are over here, right? Does that look familiar?
Yes.
You're doing like along this stretch of road here?
Yes.
And like I made that little video to kind of alert you to the fact that right here along this nice long stretch is a whole lot of geodetic control, if you're interested.
Oh, that is a nice little stretch through there.
Yeah.
Is that the railroad?
There's a railroad and there's also a frontage road, it looks like.
Yeah.
Now, somebody mentioned in a comment that it's kind of wet. You may, and like I said, I've never been out here, so I don't know what it's like to travel around out there. But that is that. This is is that the Bonneville Salt Flats, or are they somewhere else?
I don't know.
But these are old triangulation stations, and some of them have been GPSed, so you have a comparison on them. And that's this stretch here. What am I doing here? Yeah, here they are. Is that coming through okay? You can see it okay?
Yeah, I can see it real well.
I love these old triangulation diagrams. Now see the dashed lines here? That's high order leveling. It's either first order or second order leveling. So these all have elevations on them too. And if you're going to go through all the trouble in going out here, is it that much farther to get to here? And then that way you'd have some nice control you can check into.
How far apart are those points? Those three, the center three.
Let's find out.
Yeah, that's very interesting. Yeah, and the reason we're doing it where we're doing it is I wanted to do it over land and not water.
That's 71,000 feet between Desdra and Barrow. From Barrow to Arenosa is 57 something thousand feet. Not close, but you know,
No, you can put a network in between those, though.
you can only do so much, right? You know. Yeah.
Yeah, and I don't think people realize how long it takes to do differential leveling. It's
Yeah.
real time consumer.
Oh, it sure is. Get yourself a digital level. That way, at least you can move quicker, and you don't have to write it all down. And you know, and they're so accurate. They're really nice.
Yeah. Yeah.
I'm gonna do. Go ahead.
Getting one.
I want to do.
What type of digital level do you guys use?
The Trimble Dini level. It's called the Dini, D-I-N-I. What am I looking for? I want to find. There he is. Yeah, like I said, I want to leave the description of George's channel.
Target set to the height, and I have a corner reflector set up there. See?
Is the sound coming through okay?
Yeah, I can hear it just fine.
Yeah.
It's about 20 minutes after 6 p.m. on the 26th of February, and I have the laser out. I'm going to see if we can shoot and hit the corner reflector.
Nice.
There it is.
Well, that shows up really nice.
Yeah. Well, he's got quite a laboratory out here on this lake.
Wow. It's really reflecting a lot of light back. It's amazing.
Look at him driving. There's somebody out there driving. See the fishing huts, shanties?
Yeah, it reminds me of that movie, Grumpy Your Old Man.
Exactly. Well, I'll pause it there. What do you say we end it here for tonight? I'll leave the link to George's channel. You should see what he's doing out here. I really kind of want to go up there just to see it for myself. It's pretty impressive.
Yes, it is. Yeah, we can knock it off here. I still got to eat yet.
But we've been going at it for what, about maybe 2 hours? Oh, maybe close to 3.
Yeah.
I guess that can happen when you're having fun.
Exactly.
Well, Chris, I want to thank you for coming on. And let me do one last thing, just check the chat before we sign off, see if anybody's even there anymore. I got to find that. I'm seeing oh, bummer. Everybody's saying that my screen has never presented once.
Oh, no.
Yet it says right here, you are screen sharing and presenting to everyone. That's too bad. I don't know why that is. It's, huh.
So that my screen was the only one presenting?
Yeah, they've just been looking at you.
Huh.
They've hung in there too. Bummer. I don't know what to do about that because, like I said, I'm looking at in the Hangout. It says that I'm screen sharing, and it's presenting to everyone. And the only thing I can do is stop sharing. So I don't understand why they don't see it. Well, there's a bug I got to work out.
Yeah, exactly.
Anyway, we'll leave it here. Say good night. Thanks for coming on, and go do the reading I showed you there. And see if that changes your questions. You'll probably still have questions, but you might form different questions based on what you've heard tonight. That make sense?
Yes.
Yeah, good.
Yes.
All right.
Thanks for having me on. Thanks for the casual, non-attacking manner that we both presented ourselves in.
Oh, absolutely. I mean, that's how I don't know. That's how I prefer to be anyway. So no, same. I thank you too. The same thing. All right. Nice chatting with you, and we'll talk again soon.
Yes. Have a good evening.
Good evening. I'll stop.